Welcome to aminacademy.com. In strength of materials, let us discuss about crippling load on column when both ends are fixed. Look at here, this setup of this column. Consider a column AB of length L and uniform cross-sectional area and fixed at both points A and B as shown in figure. Look at here. Due to crippling load P, the column will deflect as shown in figure. Due to the fixed ends, there will be fixed end moments M0 at the point A and B. Because of the both end points are fixed, so there is a fixed moment. The fixed end moment will be acting in such a direction so that the slope at the fixed ends becomes 0. Now consider N0 equal fixed end moments and at A and B. The moments at the section is equal M0 minus Py, M0 minus Py, but moments at the section is equal Ey d square y by dx square. We know this. Equating 1 and 2 because these both moments are equal. Therefore, Ei d square y by dx square equal to M0 minus Py. Now rearranging Ey d square y by dx square minus Py go this side is plus Py equals M0. Now dividing throughout by the factor Ei, we get d square y by dx square plus P over Ei y plus M0 Ei. Now solution of this equation, that is the second order differential equation, we have y equal C1 cos x square root of P over Ai plus C2 sin square root of x into square root of P over Ai plus M0 over P. Let it be equation 3. Here C1 and C2 are the constant of integration and their values are obtained from the boundary conditions. Let us discuss about the boundary condition. At the point A, x equal to 0, due to that y equal to 0. Therefore, du by dx equal to 0 here. Also, du by dx equals 0 and A is fixed end. That means at fixed end x equals 0, y equals 0. That in equation 3 you are substituting. Equation 3 is here. We are substituting this C1 into 1 plus C2 into 0 because sin 0 is 0 plus M0 by P. Here C1 into 1 is C1. This is 0, then M0 by P. Differentiating the equation 3, that is equation is here y equal this. Differentiating this we get dy by dx equal to C1 into minus 1 sine of x into square root of P over Ei into multiplication of the factor x, x is x P square root of P over Ei plus C2 the similar cos of x square root of P over Ai into differentiation of this factor is P square root of P over Ai plus 0 because this is constant here. Now simplifying this 0 equal this 0 the C2 into square root of P over Ai where C2 equals 0 or square root of P over A equal to 0. But this factor cannot be 0, therefore here but C2 equal to 0. Then C2 equals 0, we got to the second arbitrary constant. Then we can write C1 equal minus M0 by P and C2 equal to 0. These conditions we are applying in that equation. Then therefore y equal, we are applying the conditions of equal equal to C1 and C2 we are equating that y equal to minus m0 by p cos of square root of x into square root of p over I plus 0, so that is C2 is 0 plus m0 over p. At the end b, at the end b means top end, where x equal to L total length and y equal to 0. There is no deflection at the end point, that is a fixed point. Therefore, you are substituting, that is y equal to 0 minus m0 over p cos of, instead of x you are writing L and square root of p over ai plus m0 over p. Then we are rearranging this m0 over p cos of L square root of p over a equal to m0 over p. Then cos of, because look at here, cos of L into square root of p over I, that m0 over, we go this side is as a reciprocal and cut both and it becomes 1. Therefore, cos of L square root of p over a equal to 1. We know that cos 0 equal to 1, cos 2 pi equal to 1, cos 4 pi equal to 1, like it goes. So, we'll get the cos 2 pi value. Therefore, first immediately after 0, the angle is 2 pi. Therefore, L into square root of p over ei equal 2 pi. We are equating this because here cos, cut both. Therefore, you can write L into square root of p over ei equal to 2 pi. From that, we'll get the p equal, after simplifying, squaring and simplifying, we'll get p equal to pi squared ei over L square. This is a crippling expression for the crippling load of column when both end is fixed. We have done. Please subscribe our YouTube channel.